Download this code from codegive.com, link in the description below. Part 07, Optimistic versus Pessimistic Locking, Concurrency Control in Databases. This tutorial explores optimistic and pessimistic locking, two primary strategies for managing concurrency in database systems. Understanding these techniques is crucial for building robust and scalable applications that handle concurrent access to data without data corruption or integrity issues. Understanding concurrency issues. Before diving into locking strategies, let's briefly review why concurrency control is essential. When multiple users or processes attempt to access and modify the same data simultaneously, several problems can arise. Lost updates. One user's changes overwrite another user's changes, resulting in the loss of data. Consider two users withdrawing money from the same account. If they both read the balance, then deduct their withdrawals independently, and then update the balance, the update from the first user could be lost when the second user overwrites it. Dirty reads. A user reads data that has been modified by another user but not yet committed. If the other user's transaction is subsequently rolled back, the first user will have read inconsistent data. Non-repeatable reads. A user reads the same data multiple times within a single transaction, but the data changes between reads because another user has committed changes. Phantom reads. A user executes a query multiple times within a single transaction, and the result set changes because another user has inserted or deleted rows that match the query criteria. Introduction to locking. Locking mechanisms are designed to prevent these concurrency issues by controlling access to data. They provide a way to synchronize operations performed by different transactions, ensuring data integrity. Two main approaches, optimistic and pessimistic locking. Locking strategies are broadly categorized into two main approaches. 1. Pessimistic locking. Assumes that conflicts are likely to occur. It locks data before a transaction begins to modify it, preventing other transactions from accessing the data until the lock is released. Think of it as reserving a seat at a restaurant. You know someone else might want it, so you reserve it up front. 2. Optimistic locking. Assumes that conflicts are rare. It allows multiple transactions to access the data concurrently without locking. Before committing changes, it checks if the data has been modified by another transaction since the data was initially read. If a conflict is detected, the transaction is rolled back, and the user is typically prompted to retry. Think of it as grabbing a coffee from a self-service machine. You assume nobody else is using it and proceed, but you check before actually taking the coffee to make sure nobody else has interfered. 1. Pessimistic locking. How it works. A transaction acquires a lock on a resource, example a row in a database table, before attempting to modify it. While the lock is held, other transactions attempting to access the same resource are blocked until the lock is released. The transaction performs its operations and then releases the lock, allowing other transactions to access the resource. Types of pessimistic locks. Exclusive lock. Write lock prevents any other transaction from reading or writing the resource. Only one transaction can hold an exclusive lock on a resource at a time. This is the most common type of pessimistic lock for updates. Shared lock. Read lock allows multiple transactions to read the resource concurrently, but prevents any transaction from acquiring an exclusive lock. This is useful for scenarios where you want to prevent data modifications while allowing multiple readers. Advantages. Ensures data integrity in high contention scenarios. Conflicts are proactively avoided. Simpler to implement in some cases because the database system handles the locking logic. Disadvantages Asterisk can reduce concurrency because transactions are blocked while waiting for locks to be released. Asterisk can lead to deadlocks if transactions hold locks on multiple resources and wait for each other to release them. Deadlock detection and resolution mechanisms are required. Asterisk implementation considerations Asterisk use transactions to ensure that locks are acquired and released atomically. Asterisk keep locks as short as possible to minimize blocking. Asterisk be aware of the potential for deadlocks and implement deadlock detection or prevention strategies. Asterisk typically implemented using database-specific commands, example select. For update in PostgreSQL, MySQL, and Oracle. Asterisk code example, Python with SQL Alchemy and PostgreSQL. Asterisk explanation asterisk. One database _URL asterisk replace the placeholder with the connection string to your PostgreSQL database. 2 account class asterisk defines the structure of the accounts table. 3 withdraw _money function asterisk. Asterisk takes the account _number, amount to withdraw, and the database session, DB, as input. Asterisk db.query, account.filter, account.account _number equals account _number, .with _for _update, .first, this is the crucial line. It selects the account row with the specified account _number and acquires an exclusive lock on it before returning the row. The with _for _update option tells SQL Alchemy to include a for update clause in the SQL query, which instructs PostgreSQL to lock the selected row. This lock will prevent other transactions from modifying the row until the current transaction commits or rolls back. Asterisk the function then checks if the account exists and has sufficient funds. Asterisk if both conditions are met, it updates the account balance, commits the changes, and prints a success message. Asterisk if any error occurs, it rolls back the transaction and prints an error message. 4 simulate _withdrawal function asterisk. Asterisk takes account number and amount as input. Asterisk creates a new database session, calls withdraw _money to execute the withdrawal, and then closes the database session. This ensures that each thread has its own database connection and that connections are properly closed after use. 5 if _name equals main block asterisk creates an initial account in the database with a balance of 1000.0. Asterisk creates 2 thread objects, each configured to call the simulate _withdrawal function with different withdrawal amounts, 200.0 and 300.0, for the same account, 1 2 3 4 5. Asterisk starts the threads, allowing them to run concurrently. Because of the pessimistic lock, one thread will acquire the lock first, perform the withdrawal, and release the lock. The other thread will then acquire the lock and perform its withdrawal. Asterisk the thread 1.join, and thread 2.join, calls ensure that the main thread waits for both withdrawal threads to complete before proceeding to the final balance verification. Asterisk finally, it retrieves the updated account balance from the database and prints it to the console. This balance reflects the result of both withdrawals, ensuring that the withdrawals are executed correctly even in a concurrent environment due to the pessimistic locking mechanism. 6 key point asterisk because of the with _for _update lock, the second thread will wait until the first thread completes its transaction, commits or rolls back. This ensures that the balance is updated correctly and that no money is lost. Asterisk to run the code asterisk. 1. Make sure you have PostgreSQL installed and running. 2. Create a database named MyDB, or change the database _URL accordingly. 3. Create a user with the username user and password, or change the database _URL accordingly. Grant the user appropriate permissions on the database. 4. Install SQL Alchemy and Psycha. Page 2, the PostgreSQL adapter pip install scalable Psycha. Page 2 binary. 5. Run the Python script. You should see output indicating that the withdrawals were successful and the final balance is correct, 1000 to 200, 300 equals 500. 2. Optimistic locking. Asterisk how it works asterisk. Asterisk a transaction reads data without acquiring any locks. Asterisk the transaction performs its operations and prepares to commit changes. Asterisk before committing, the transaction checks if the data has been modified by another transaction since it was initially read. This check is typically done by comparing a version number, timestamp, or checksum. Asterisk if the data has not been modified, the version number, timestamp, or checksum matches, the transaction commits its changes. Asterisk if the data has been modified, the version number, timestamp, or checksum does not match, the transaction is rolled back, and an error is raised. The user is usually informed that the update failed due to a concurrent modification and asked to retry. Asterisk advantages asterisk. Asterisk increases concurrency because transactions are not blocked while waiting for locks. This can significantly improve performance in low contention environments. Asterisk avoids deadlocks because no locks are acquired. Asterisk disadvantages asterisk. Asterisk requires application logic to handle conflicts and retries. The application must be able to gracefully handle the update conflict error. Asterisk can lead to wasted work if transactions frequently fail due to conflicts. This is more likely in high contention environments. Asterisk may be more complex to implement correctly than pessimistic locking, as it requires careful management of version numbers or timestamps. Asterisk implementation considerations asterisk. Asterisk add a version number, or a timestamp or checksum, column to the table being protected. Asterisk when reading data, store the current version number. Asterisk when updating data, include the version number in the where clause of the update statement. The update statement should only succeed if the version number in the database matches the version number stored by the transaction. Asterisk if the update statement fails, returns 0 rows updated, it means that another transaction has modified the data in the meantime. Roll back the transaction and inform the user. Asterisk code example, Python with SQL Alchemy and PostgreSQL. Asterisk explanation asterisk. 1 database _URL asterisk replace the placeholder with the connection string to your PostgreSQL database. 2 account class asterisk added a version column to the accounts table. This integer column is used to track the version of the row. It is initialized to 0. 3 withdraw _money _optimistic function asterisk. Asterisk account equals db.query, account, dot filter, account _number equals account _number, dot first, retrieves the account row without acquiring any locks. Asterisk current _version equals account.version, stores the current version number before attempting to modify the account. Asterisk account.balance equals amount, decreases the account balance. Asterisk account.version plus equals 1, increments the version number. This is important because the incremented version will be committed to the database, which will indicate that the row has been modified. Asterisk db.commit, attempts to commit the changes. If another transaction has modified the row in the meantime, a stale data error will be raised. This error is automatically raised by scalable session management when an update statement affects 0 rows. The update statement will have a where clause that checks the version number, and if the version number in the database does not match the version number in the where clause, the update statement will affect 0 rows. Asterisk accept stale data error, catches the stale data error and rolls back the transaction. This indicates that another transaction has modified the row in the meantime. A message is printed to the console. For simulate _withdrawal _optimistic function asterisk. This function introduces retry logic to handle potential stale data error exceptions that can occur due to concurrent updates. If withdraw _money _optimistic returns false, indicating a conflict, the function waits for a short, random amount of time, to avoid immediate retries and potentially further conflicts, and then retries the operation. The retry loop is limited to a maximum number of attempts, example 3 retries. If the withdrawal still fails after the maximum number of retries, the function prints a failure message. 5 usage example. Initialized the version number to 0. 6 key point *. The stale data error is raised when the update statement in the db.commit call affects 0 rows. This indicates that another transaction has modified the row in the meantime, and the current transaction should be rolled back. The application logic is responsible for handling this conflict and retrying the operation or informing the user. To run the code *. 1. Make sure you have PostgreSQL installed and running. 2. Create a database named MyDB, or change the database _URL accordingly. 3. Create a user with the username user and password, or change the database _URL accordingly. Grant the user appropriate permissions on the database. 4. Install SQL Alchemy and Psychopage 2, the PostgreSQL adapter pip install sclalchemy Psychopage 2 binary. 5. Run the Python script. You may see optimistic locking conflict detected messages if the threads attempt to update the same row at the same time. The final balance should still be correct, 500.0, and the version should reflect the number of successful updates. The output may vary depending on the timing of the threads. Choosing between optimistic and pessimistic locking. The choice between optimistic and pessimistic locking depends on several factors. Contention if contention for data is high, i.e., updates are frequent, pessimistic locking is generally a better choice. It avoids wasted work and ensures data integrity. If contention is low, i.e., updates are infrequent, optimistic locking can improve concurrency. Response time optimistic locking can provide better response times because transactions are not blocked while waiting for locks. Complexity pessimistic locking is often simpler to implement because the database system handles the locking logic. Optimistic locking requires more complex application logic to handle conflicts and retries. Application requirements some applications require strict data integrity and cannot tolerate any possibility of conflicts. In these cases, pessimistic locking is the preferred choice. Other applications may be more tolerant of occasional conflicts and prioritize concurrency. Summary table Feature pessimistic locking optimistic locking. Locking strategy locks data before modification. Checks for modifications before committing. Conflict assumption conflicts are likely. Conflicts are rare. Concurrency lower concurrency due to blocking. Higher concurrency, no blocking. Deadlocks possible deadlocks. No deadlocks. Complexity simpler to implement, database handles locking. More complex, application handles conflicts/retries. Response time can be slower due to waiting for locks. Can be faster, no waiting. Use cases high contention scenarios, strict data integrity required. Low contention scenarios, concurrency is a high priority. Conclusion. Optimistic and pessimistic locking are important techniques for managing concurrency in database systems. Understanding the trade-offs between these approaches is crucial for building robust and scalable applications. Carefully consider the characteristics of your application and the expected level of contention when choosing a locking strategy. Remember to choose the right tool for the job. Also, understand how your specific database system implements locking features. The code examples provided are meant to illustrate the general concepts, but the details of implementation may vary.